evening everybody. So, we are still with the bonding for the different metal complexes, and in this part we have been seeing that how the different d orbitals which are of same energy undergoing splitting within a crystal field. So, if we put the corresponding crystal field, how the ordering of the different d orbitals will change and in which particular symmetry the orientation would be of one type and in another symmetry the orientation can be of different type. So, we will see that this bonding in complexes of part 3, that crystal field theory what we have seen, it can be used to describe particularly the different types of spectroscopic assignments of the different transition metal complexes. So, if we see the corresponding spectroscopic signature of all these metal complexes, so how we can classify them in terms of this particular theory. So, here we are basically assuming that a particular metal ligand interaction is purely electrostatic in nature, and that is why we think that everything is within a environment where a crystal is operating. So, in a particular octahedral crystal field, so we have all the different types of orbitals, the metal ion orbitals which is sitting inside a cube, and if we just consider the different types of these interactions and which are all electrostatic in nature, and if we consider the metal ion has all the s orbitals, then the p orbitals and the different d orbitals, and since the d orbitals are the outermost orbitals, so we will mainly focus our attention on the interaction of the d orbitals with these dipoles of the 6 ligands, and these dipoles or the negative ends of the ligands are facing towards this particular metal center from the 6 faces of the cube, and which is basically giving rise to the corresponding octahedral geometry. So, center of each and every face is occupying the ligand, and this particular ligand is then interacting directly with the metal orbitals, and this particular interaction can give rise to a particular type of splitting, and that splitting we will call as the crystal field splitting. So, this particular theory basically tells us that how crystal field theory telling us that the corresponding splitting of the different d orbitals will take place in a particular symmetry. So, if we have the spherical environment, so in the spherical environment, so energy of all the 5 d levels will be raised. So, the crystal field which is spherical in nature, so this particular spherical crystal field is operating on this particular 6 d levels, and these 6 d levels then will undergo splitting into 2 sets. One is the corresponding T2G set and another is the corresponding T2G set. So, in this particular class we will just consider the different spherical arrangement. So, if the arrangement is from a octahedral field, we will get the corresponding splitting, and the amount of splitting with respect to the unsplitted barycenter, which is the center where we have the corresponding energy level, in which particular case we do not have the splitting. So, before splitting we have some energy level for the d level, and after splitting we have some of these orbitals will have some lower energy and some of them are going up, and the entire amount of this particular splitting, that the separation between these two levels, one we call it as the T2G level and another we are calling at the EG level. So, the separation between this T2G and EG level is known as the corresponding crystal field splitting. So, this is the corresponding crystal field splitting parameter or splitting energy for the octahedral crystal field, and we will find out that how we determine this particular amount of stabilization for the T2G set, which is 2/5 delta 0, and the amount of destabilization for the EG set will be 3/5 delta 0. So, this particular theory successfully accounts which the previous one, that means the valence bond theory, could not explain for some magnetic properties. So, some of the magnetic properties we can explain nicely, which we could not explain through valence bond theory or VBT. Then the color of the compounds, then hydration enthalpies, because most of these salts what we have seen, when you dissolve these salts, particularly the chloride salt or the sulphate salt or the nitrate salt in water, they form the corresponding hydrated complexes or the aqua complexes. So, how these hydration enthalpies are getting changed through this particular type of hydration, that can also be determined from the corresponding crystal field stabilization energies. Then the splinel structures, that means the corresponding mixed oxides, the mixed oxidation states of the oxides, and some of these oxides are present with some spheres in tetrahedral field and some of them are in octahedral field. And if these two fields are predominating, then we can find out which particular metal ion, whether the bivalent or the tetravalent, such as Fe3O4, which is a mixed valent spinel structure. So, that particular structure, whether the ferrous ion will be in the tetrahedral field or the ferric ion in the tetrahedral field, that can be determined if we find out the corresponding of occupancy of those metal ions in the different environments. So, the spinel structure can also be explained in terms of the corresponding metal complexes, but in most of the cases it does not attempt to describe the typical nature of this bonding. So, for the exact bonding nature we have to use the corresponding other type of theory, where the crystal field theory can be mixed up with the that corresponding molecular orbital theory, and that molecular orbital theory will account for the corresponding ligand field theory. It is Hans Bethe and John Hansbrook Van Vleck. These two people, and they are basically the physicists, they considered this corresponding interaction in terms of the corresponding crystal type of interactions, and they developed and proposed this particular crystal field theory in and around 1930s. So, these two people basically considered as the father of the crystal field theory, and this particular theory subsequently combined with molecular orbital theory to form the more realistic and complex ligand field theory. So, ligand field theory would be a little bit complex one, where we will find that most of this part belongs to the molecular orbital theory, but it can be explained for some of its part as the corresponding crystal field theory. That means, the crystal field theory can be derived from the ligand field theory for some basic explanations like magnetic properties, the color and the spinel structure or the hydration enthalpies, and which therefore delivers insight into the process of chemical bonding in transition metal complexes. So, in some of our future classes we will be considering this particular theory to know the exact nature of the bonding in transition metal complexes, whereas we have the corresponding donation from ligand to metal or the metal to ligand back bonding. So, before that we will just focus our attention on the corresponding crystal field stabilization. So, for a D1 system, so in D1 system in octahedral field, if we have the system in octahedral system, what we find that the overall we have all the 5 d orbitals. So, on the left hand side we have 5 d orbitals, and the energies of these 5 d orbitals are basically, when we consider that altogether we have 10 electrons. So, 5 d orbitals means we have therefore 10 electrons, and these 10 electrons can have the corresponding occupancy before the splitting and after the splitting also. So, we have the corresponding crystal field in a typical octahedral geometry, where we find that if this particular energy we can have, that means one is x and another is y. So, we can have 4 electrons here, the occupancy can be 4 electrons. So, if this is x and this is y, then we can have these altogether 10 electrons will be distributed between these two levels. One is T2G level, another is the corresponding EG level. So, these two levels we have. So, the upper one would be therefore E plus x, because this is the energy for this particular level, the unsplitted level is E, and the lower would be E minus y. So, this particular case what we find that the T2G level and the EG level has the total of 4 electron and EG level has 6 electrons. So, altogether these electrons we can have, which give rise to the equivalency of 2x with 3y, and the entire this x plus y value is nothing but the corresponding crystal field splitting in octahedral geometry. Therefore, by combining these two, we get x is equal to 3/5 delta octahedron and y is equal to 2/5 delta octahedron. So, if x plus y is equal to delta octahedron is equal to 10 dQo, also we explain in some cases this as 10 dQo, then this would be equal to 6 dQ octahedron and this equal to 4 dQ octahedron. So, we have therefore the T2G electron, these T2G electrons are therefore in this particular level. So, T2G electrons they are in this particular level are stabilized. So, each of them is stabilized by minus 4 dQo. That means, it is stabilization which is lower in energy, and therefore, the reverse, that means each EG electron which are in the upper level would be destabilized by plus 6 dQo, and all these are with respect to the barycenter, which is our this one. So all these are therefore with respect to the unsplit barycenter. That means the total energy of the system is conserved before and after splitting. And we have these two levels which we are considering, one as the T2G level and another as the EG level, and in these cases the E stands for the corresponding twofold degeneracy, and T stands for the triplet one. This is therefore twofold means doublet one. So, the degeneracy is doublet, and here the T stands for a threefold degeneracy or triplet. And this G basically, the other level is there is G. G is related to the symmetry, which is Gerade, which means even. That means the metal ion which is sitting inside the octahedral environment, which is at the center of inversion I, which is center of inversion. That means if we transform, that means if we go for the corresponding symmetry operation with respect to this I operation, we will get the same sign of the wave function and the same molecule. That means the environment, if we have all L at all these positions, they are even in nature, that is why the level is G. But when we will be moving for the corresponding tetrahedral symmetry, in TD symmetry, I is not there. So, we cannot level those orbitals which will be splitting within a tetrahedral crystal field as a corresponding level as G. So, G will be dropped there. Similarly, this is also even with respect to the corresponding inversion symmetry operation, and this particular value 2 is also related to an C2 operation for this corresponding symmetry. So, these are the corresponding symmetry levels with respect to the corresponding inversion. So, what we do with respect to center of inversion, the d orbitals basically maintain same sign of their wave functions. That is why under this crystal field, the two sets of these orbitals, the T2G set and the EG set, will be leveled with a level which is known as the corresponding G level, that means the even level. So that basically gives us some information that already we have seen that we can have the sets of T2G as dxy, dyz and dxz, and EG set is dx square minus y square and dz square, and we have the corresponding delta and delta O. This is basically for this. So only 3 orbitals will be available which are degenerate for the corresponding occupancy of the electron when we have the corresponding crystal field splitting, and for the electronic configuration D1, the D1 system, it can be 3D1, can be 3D 4D1 or 5D1. We have the corresponding electronic configuration which can be labeled as T2G1. Since the other level is available for this corresponding occupancy for the single electron, so we can promote these single electron which are in the T2G level to the EG level, and there will be corresponding transition, and we have the corresponding absorption, and we get the corresponding color for the compound having this particular electronic configuration. So when light of wavelength of 510 nanometer is passed from this particular configuration, is passed through this electron configuration, the electron in the T2G level can be promoted to the EG level, and we have the corresponding absorption as 510 nanometer and the corresponding color. So 510 nanometer is the corresponding color range for the visible region and which will be absorbed, and the corresponding color of the solution would be its complementary color, and we observe all these as the solution color would be the corresponding complementary color of the solution due to this transition. So continuously this can relax back to the ground state. Again we can push the electron from the lower level to the higher level, and this basically considered, which is not allowed though, as the typical D to D transition. We will all consider it is a DT transition. So that is why the crystal field theory can explain to some extent the corresponding DD transition for the origin of the color for the different complexes. Then we will see that this delta, whether it can be labeled as with a subscript O means for octahedron and T for the corresponding tetrahedral symmetry. Therefore, the crystal field splitting energy corresponds to the light wavelengths in the visible region of the spectrum. That is why the h nu value or the E value for the corresponding wavelength what we are focusing on the solution is all in the visible region. That is why most of these compounds would be colored, and there will be a change in color if we change the corresponding ligands. That we have seen that around nickel, if we have all the 6 water molecules, we have a typical color, and through ligand substitution, if we replace all the 6 water molecules by ammonia, we will get a color change. Then all the 6 ammonia molecules by 3 ethylene diamine, we again see some color change. So the 3D1 configuration belongs to the hexa-aco titanium 3 plus cation. So this is the corresponding aco complex of titanium in trivalent state, which has one and only one d electron in lower energy orbital, that means the T2G level, and 500 to 510 nanometer of light absorption can take place for the promotion of the electron from the T2G level to the EG level, and that is why the titanium solutions can show the corresponding absorption in this particular region. So any compound, whether we prepare it from titanium chloride or titanium nitrate or any other source of titanium, if we dissolve it in water or a water solution is made, and if we suspect that the corresponding hexa-aco titanium compound is generated in the solution, we run the corresponding electronic spectrum and see the typical absorption. So the nature of the absorption band and its corresponding lambda max value in the range of 500 to 500 nanometer will immediately tell us that the species present as a complex species, as a complex compound in solution, is the corresponding hexa-aco titanium 3 ion. So, we just then responsible for this particular transition, and light absorption can take place, and we can promote this electron either to dz square or dx square minus y square. So, this absorption spectra of different complexes therefore indicate that the crystal field splitting energy depends on the nature of the ligand. So, if we have the corresponding metal ion surrounded by water molecule or surrounded by ammonia or ethylene diamine. So, the corresponding absorption energy, the corresponding absorption will depend on these nature of these ligands. So, the nature of the ligand is therefore very much important to see the corresponding absorption. So, for Ni2 plus complex, delta increases as the ligand is changed from water to ammonia to ethylene diamine. That means, we will be increasing the delta value, that we will see how we can order the different delta values for all these particular spectral change. So, in case of if we have the corresponding red line as the corresponding energy scale, we have the hexa-aco nickel 2 plus, and we get the corresponding separation between the T2G set and EG set, and we have a nickel 2 plus means is a 3D8 system. That means 8 electrons to be placed in all 5 D levels. So, this is the corresponding spin state, that means all the levels in the T2G level are filled, and we have 2 unpaired electron in the EG level. So, the separation between these two will be changing as we go from the green solution of hexa-aco nickel 2 plus to blue solution, where the separation is bigger compared to the water molecule. That means, we can also correlate to be a solution to be seen as blue, the corresponding lambda max for the absorption for the crystal field transition would be of higher energy, that means lower wavelength. Similarly, if we move from blue hexaamine nickel 2 ion to violet tris ethylene diamine nickel 2 ion, we will get the delta is far more higher, the separation is bigger compared to the amine complex also, and we will have more energy requirement for transition of the electron from the lower level to the upper level. So, we can push this electron say to this particular level, and the amount of energy required for that particular transition will be given by the delta value, and this is will be known from measurement of the simple electronic spectra. So, if we measure the electronic spectrum, we will be able to tell that why this particular solution is violet, but not green, which is for the corresponding hexa-aco compound. So, ligands which cause a large splitting of delta value of the d orbitals are referred as corresponding strong field ligands. So, some of these ligands we will be considering at the strong field, that means it is providing us a corresponding crystal field which is strong enough, and as we move, such as in case of nickel, we just see the corresponding separation is changing, the separation is increasing as we move from water to ammonia to ethylene diamine. That means, ethylene diamine has a strong ligand field compared to the water molecule, once we know the corresponding separation between these levels. So, there are some complexes such as that of the corresponding nitrite ion, they called as they call low spin. For example, NO2 minus is a strong field ligand and produces a large delta value. So, like ethylene diamine around nickel 2 plus, this NO2 minus say around iron 3 plus can provide a corresponding strong field environment, and the delta value is higher. So, up till now we can define that the corresponding field is strong enough if we see that the delta is bigger and if the delta is small, we count is the corresponding weak field strength for the corresponding ligands. So, if delta octahedron delta O is large, we see for a electronic configuration of 3D or 4D or 5D 5, that means 5 electrons are there, and if this is large, that means this delta O is large, these two electrons instead of going to this Eg level, they will be paired off. That means this delta value is higher than the corresponding pairing energy for pairing in the T2G level. That means we have less number of unpaired electron. If we do not have the corresponding pairing in these two levels, we have this electron in this level and this electron also in this level. So, altogether 1, 2, 3, 4 and 5 unpaired electrons we are having. But since this delta is large, we will push those two electrons from this Eg level to the T2G level downward, and this will reduce the corresponding number of available unpaired electron from 5 to 1. That means we get a corresponding compound which are known as the low spin compounds. So, we have therefore, that means we have, if we have the large splitting of delta, the crystal field is large enough, we will push those electrons from the upper field to the lower one, and we get basically low spin compound. That means low spin compounds are those compounds where the available number of unpaired electrons are small. This is the situation for a low spin compound of iron 3, which is FeNO2 6 3 minus, and this can be considered at its corresponding crystal field diagram, where we see the corresponding number of electrons in this level is T2G 5 only. So, simply we have the T2G 5 electronic configuration for this iron, and we get the corresponding low spin compound. Similarly, the other two ligands like iodide and bromide, if we compare them with nitride, they cannot cause very large splitting as we have seen in case of nitrate ion. So, bromide and iodide, that means the corresponding bromo and iodo compounds of iron, we have a splitting which is less than that we have observed just now for the nitrate complex. So, small splitting of delta of the d orbitals will be considered as the weak field ligands, and as a result high spin complexes result. That means whatever compound we will be getting with iodo and bromo ligand, they are all of high spin. That means the maximum number of unpaired electrons can be there. So, all the 5 levels, the T2G level as well as the Eg level, all will be singly occupied. So, there are 5 electrons, 3 in the T2G level and 2 in the Eg level, and all will be singly occupied. That if we write them as the off spin, that means we have 5 unpaired electron, and the magnetic moment, the determined magnetic moment would be high also, which will correspond to 5 unpaired electron, which was not possible in case of the corresponding low spin compound. So, this is FeBr42 minus, so the hexabromo ferric 3 ion and its crystal field diagram showing that the compound is a high spin compound. So, now if we move to the tetrahedral field, and in this particular tetrahedral field we will find that the situation is changing now, because in case of the corresponding octahedral field, we are just looking at the 4 plus 2, 6 faces, and the center of the faces are occupied by the ligands. Now, to generate a corresponding tetrahedral field, which is TD crystal field, the TD crystal field will have alternate corners would be occupied by the ligands. and center of this cube will be occupied by the metal ion. So, we get the corresponding crystal field, and you see these L are the 4 ligands, and within the cubic field, because this is also a cubic field, and within this particular cubic field, if we place all these 5 d orbitals, we will see like that of our octahedral geometry, that they will now face differently. In earlier case, we have seen that the ligand is here for octahedral geometry, ligand in all 6 faces of the corresponding cubic geometry, and they are directly facing the dx square minus y square and dz square orbital. That is why they are mostly destabilized, and we get the corresponding EG set in octahedral geometry. But in this particular case, these are half diagonal distance. You have this diagonal of the one cube face, and it is pointing towards the center of this particular face. So, its half diagonal distance is facing one particular ligand to the lobe of dz square orbital or the dx square minus y square, because this is the corresponding x direction and this is the corresponding y direction. Again, if we look at this particular face, it is pointing towards the half diagonal distance from the ligand. So, they will be most stabilized compared to the other 3 orbitals, and these two belong to the E set now, and G will be dropped from their nomenclature because we do not have the corresponding center of inversion with respect to the metal ion center. So, with respect to the inversion operation, it is not even, it is the odd symmetry, and that odd symmetry will be designated as any no level as G as its subscript. Similarly, these particular orbitals which are facing in this edges of this cube. So, this is the half edge distance. So, they are facing the dyz, dxz and dxy. So, half of this edge basically, and half of this edge is nearer compared to half diagonal distance. So, half edge distance is shorter compared to half diagonal distance. That is why all 3, that means dyz, dxz and dxy orbitals will face these orbitals strongly, and that is why we have the higher energy T2 set, not T2G. This will be labeled as T2 for their interactions. So, this is basically the exact drawing of the corresponding tetrahedron. So, this is the tetrahedron, and we have either the negative ligands, negatively charged ligands, or the negative end of the dipolar units compared to the octahedral geometry, because if this is the octahedral geometry, means all 6 faces are occupied, but here alternate coordinates will be occupied for the corresponding tetrahedral geometry. And once we place all the d orbitals within the field, we will find that these are basically corresponding levels, that means this will be the corresponding E set. So, this will be stabilized because we have the half diagonal distance compared to the half edge distance. So, this is the half edge distance, and half edge is obviously is also very much pointing towards this particular point where we do not have any ligand here. So, if we consider these 2 ligands in this particular direction, which is the corresponding diagonal distance, that means this is the corresponding diagonal distance, and the ligand lobe is facing halfway from this particular edge. So, they are the corresponding thing, that means they are little bit nearer than that corresponding ligand system, and they will be therefore destabilized. So, this is like that of our octahedral symmetry. This is the corresponding symmetry geometry for the tetrahedral thing, and we have the corresponding ligands along these 4 coordinates of this cube, and we have the corresponding splitting. So, this splitting is completely different from that of the octahedral splitting, and we have now the E set and the T2 set, and the corresponding splitting is known as corresponding delta T, either capital T or the small t. So, this delta T will be there, and if we just simply consider that corresponding to the octahedral environment, that this will be stabilized by 3/5 of delta t, and this will be destabilized by 2/5 of delta t, which is exactly the reverse one as we have seen for the corresponding octahedral geometry. So, here we just also see that this particular destabilization with respect to the barycenter is due to the corresponding electrons in this level, and the other cases the corresponding electrons in the T2 level. And since fewer number of ligands are facing the metal ion compared to the octahedral geometry, we have only 4 ligands. So, the interaction with the metal center is less, and the less interaction is also responsible for the corresponding amount of splitting, and this particular crystal field splitting would be therefore less compared to any octahedral splitting. So, it is 4/9 times to that of any octahedral crystal field splitting if we consider the same situation for the same metal ion and the same set of ligands. If we want to compare the splitting what we see for the octahedral symmetry and the tetrahedral symmetry, the tetrahedral symmetry we have the less amount of splitting, and that is why in tetrahedral symmetry we do not get any low spin complexes. Since the splitting is less, most of the cases or all the time we get only high spin compounds. Therefore, this is the 4/9 of the corresponding splitting, and the corresponding splitting energy for the tetrahedral metal complexes where we have 4 ligands is referred to as delta capital T, delta small t, or delta tet. All is there, we can write anything of them, and is roughly equal to 4/9 of the delta oct or delta O, that means the octahedral one for the same set of metal ion and the same ligand system. So, we get almost basically half of the corresponding splitting what we observe for the corresponding octahedral splitting. And therefore, we have the corresponding crystal field stabilization, and we can calculate out the corresponding crystal field stabilization energy, which can also be applicable to other transition metal complexes. So, the different types of transition metal complexes we can have in different geometries, the way we have seen the corresponding geometries for the octahedral geometry. This is for the octahedral geometry, this is for the tetrahedral geometry. Now, if we can go for the other type of geometries, we will find that there are also the corresponding splitting. So, if we have a corresponding pentagonal bipyramidal geometry, this pentagonal bipyramidal geometry, what we will find that we have in plane a pentagon and one ligand above this pentagonal plane and one ligand below this. So, we have 5 plus 2 7 ligands around the metal center, and we have therefore the corresponding interaction with these orbitals, that means the 5 d orbitals. Since these two, that means the corresponding these two which are in z direction, and we can consider that along this z direction we have these corresponding ligands, and they are facing directly the dz square orbital. So, this ligand and this ligand will be facing this particular d orbital along this particular z axis, and their interaction is very high. That is why dz square orbital is mostly destabilized with respect to the corresponding crystal field splitting. And then the other two orbitals which are in the xy plane, that means dx square minus y square and dxy, they are basically in this particular plane, that means the pentagonal plane. So, if the pentagonal plane is in the xy plane, so these two orbitals basically will be next destabilized by facing 5 ligands within this plane. So, we have 4 plus 4 8 lobes for xy and dx square minus y square orbitals, and they are equally sharing the corresponding points along the pentagon in this particular plane. So, they are the second destabilized ligands with respect to the dz square. So, the remaining two which are having the z components, the xz and yz, so they will be in between. So, they are along the z direction in x plane and the y plane. That means they are having the z components. So, the orbitals having the z components in a set of dxz and dyz, they are the most stabilized one. So, since they are not directly facing any of the ligand which are in this particular plane, since these two orbitals are away from the plane, that means they are away from the z axis and also they are away from the xy plane, they will be mostly stabilized for their corresponding separation from this particular splitting. So, the pentagonal bipyramidal geometry will give rise to a corresponding separation like this. That means the dxz and dyz will be most stabilized one. So, this is basically a doublet set. Then another doublet set, we have the dxy and dx square minus y square. So, these two are E set, this is E set, this is E set, and we have the final set which has dz square, which is the singlet state, which can be labeled as small a. So, we can have another geometry for the square antiprismatic geometry, which is a corresponding geometry is a complex one, antiprismatic geometry square. So, if we have the square prism, which is nothing but the cube geometry, and if we have this is the corresponding square antiprismatic geometry, and if we put all the orbitals, that means we have the metal ion here and which has the corresponding 5 d orbitals. So, all those 5 d orbitals will have different types of interactions from the ligands along these directions. And we get some kind of interactions where the ligands which were mostly stabilized in pentagonal bipyramidal geometry will be destabilized in this particular case. That means dxz and yz are mostly destabilized. Then we have the dxy and dx square minus y square, and finally the most stable arrangement is dz square, because this will not face any of the ligand in square antiprismatic geometry. So, interestingly, like that of the situation what we have seen in case of the octahedral and tetrahedral geometry, that one particular type of splitting is the reverse to the other. Similarly, this pentagonal bipyramidal geometry having a coordination number of 7 and square antiprismatic geometry with a coordination number of 8, they have the similar type of reverse relationship. That means here the dz square is mostly destabilized, here the dz square is stabilized, and these two are the stabilized orbitals, here it will be most destabilized orbitals. So, is the reverse relationship we can have with this type of splitting for square antiprismatic geometry. So, if we now then move on to a geometry like square planar, which is mostly a interesting geometry for us, because whatever ligand we were just seeing, that in case of a particular octahedral geometry, what we see that these are the two L along the z axis. So, along the z axis, if we can have these L, and if we just simply remove all these L from this z axis, we will be remaining with only these 4 ligands in a square planar. So, we will end up with a square planar geometry. So, those orbitals which are interacting with the ligands along z axis will no longer be there. That means, if we remove these L, these two L, these two ligands to an infinite distance along the z axis, we will end up with a square planar geometry from an octahedral geometry. So, any octahedral geometry can give rise to a corresponding square planar geometry if we move these two L from a particular intermediate ML distance to an infinite distance, and that basically gives us the corresponding splitting like this. And this particular splitting we can have from the corresponding octahedral splitting also. So, that T2G set and the EG set we can have, and there we have seen that dx square minus y square and dz square were the EG set, and T2G is dxy, dyz and dxz levels. So, now if we just remove these two groups from above this particular square plane and below this particular square plane along the z axis, that means the z components, the orbitals having z components will be mostly stabilized. That means dz square and dyz and dxz will be stabilized. So, they will form basically the ground level with some separation, but the orbitals which are in the xy plane, if we consider that xy plane is the corresponding molecular plane, that means where we have the 4 ML bonds, that means within the xy plane we have 1 metal ion and 4 ligands. So, 1 metal ion and 4 ligands will give rise to the corresponding square plane, and in this particular square plane we have the most destabilized orbitals would be the dx square minus y square, because these ligands facing the metal ion along the x along the y axis. So, they are directly facing the x square minus y square orbital. So, that particular orbital is the most destabilized one, and the intermediate one is the corresponding dxy orbital, which is in between x and y axis, and this will be the next one. So, we have the corresponding separation. So, we have one separation here, we can have another separation between these two orbitals, and the third type of separation is between dxy and dx square minus y square. So, most of these cases, particularly the nickel 2 plus in square planar geometry, we find that these compounds are diamagnetic in nature, because in that particular case these 4 orbitals would be available like from the valence bond picture as the dsp2 hybridization. So, these 4 orbitals will be available for occupying the 8 electrons available for nickel 2 plus. So, here 2, here another 2, and lastly the last 2 electrons would be in the dxy. So, we do not have any electron in the dx square minus y square level, and the molecule will become a diamagnetic one. So, we have the corresponding situation like this, where we have from the octahedral geometry. So, if we just move from the octahedral geometry, we remove these two, that means we remove this L. So, this particular along the z axis, if we remove, then so the situation will be, the corresponding situation is would be known as z out situation. So, when z out situation is there, we have the T2G and the EG level. So, when we are removing this, so when z is taking away from the environment, and here we have dz square. So, this thing which will be stabilized will be z square, and x square minus y square will be above. Similarly, for the T2G set, which belongs to the YZ, XZ and XY, so we will have separation like this. That means, since it is in the XY plane, this particular plane is X and Y. So, the component which are having both X and Y, that means the dxy would be mostly destabilized with respect to the T2G, and the other two will be here, which are YZ and XZ. So, this is basically not the final situation, which is only the Z out situation, where we have ML distances are longer compared to the other ML distances which are present in the XY plane. So, when we take this Z, that means Z's are moved to some infinite distance, we will end up with a square planar environment, and in that particular situation this particular ligand has been removed, this particular ligand has been removed, and in that particular case the Z square is further stabilized and XY is further destabilized. Similarly, XY is further destabilized and these two are also further stabilized. So, our splitting is changing and we are ending with a corresponding compound for the square planar environment, and we are having basically the separation between this dx square y minus y square and dxy as the corresponding most important crystal field splitting parameter for the square planar environment. That is why any D8 complex in this particular case will all be paired in these 4 levels and we will get the diamagnetic compound. Though we have 1 separation, 2 separation and 3 separation, but it will be mostly controlled by this particular separation between dx square minus y square and dxy level, and that will push this electron from this level to that level, and all 4 orbitals will be paired up and we get a diamagnetic situation for nickel 2, palladium 2 and platinum 2. Thank you very much.